Welcome to the Deep Dive. Our mission today is a journey into, well, really the future of medicine, where AI isn't just analyzing biology anymore, but actively creating it.
That's right.
For years, the whole conversation around AI and drug discovery was about prediction. What will this existing protein fold into?
Yeah, that was the big question.
Now, that discussion has fundamentally shifted.
Yeah.
We're deep diving into these revolutionary advances in AI-driven biomolecular design AI that invents brand new functional molecules, moving completely beyond the evolutionary rulebook.
And we have a stack of sources here that are, they're just dizzyingly technical. They cover everything from foundational physics and deep learning architecture all the way to, hard wet lab validation.
This is probably the most complex space in AI right now.
Arguably, yes. So our goal is to really pull out the key insights that explain how these models, like the generative model Boltzgen, or these new confidence metrics like CODE, are letting AI design molecules that have quite literally never existed before, and do it reliably.
Okay, so let's unpack that. If you're going to design something totally from scratch, you can't just throw atoms together randomly. The AI model, it has to respect the fundamental laws of physics.
It has to.
And the foundation of this whole revolution, it seems to rely completely on molecular symmetry.
That's exactly where we have to start. When you look at physics, especially at the scale of atoms, of molecules, symmetry is everything. And when we talk about symmetry in computation, we usually talk about two concepts, invariance and equivariance.
Right, and I think invariance is the easier one for people to get their heads around.
Oh, absolutely. Invariance just means the output stays the same no matter how you transform the input. So take a protein's potential energy.
Okay.
If you pick up that protein and just rotate it 90 degrees in space, the energy that's stored in its bonds doesn't change at all.
So the output, the energy is invariant to the input, the rotation.
Exactly. But equivariance is the really critical piece for design because design involves, movement and placement.
It's dynamic.
It's dynamic. Equivariance means that when you transform the input, the output transforms in a predictable way. Think about the vectors of an atom. Its position, its velocity, the forces acting on it.
Right.
If you rotate a molecule 90 degrees, every single force vector on those atoms must also rotate exactly 90 degrees. If your AI model breaks that rule, you've just created something that violates physics.
And it just won't work. It won't fold. It won't function.
It won't work. So you have to build those rotational laws directly into the neural network's architecture itself.
And that's the whole innovation behind these new tools, right? Like equivariant graph neural networks, EGNNs.
Precisely. They are built from the ground up to enforce this rotational symmetry, specifically it's called SO3, rotational equivariance, at every single step of the calculation.
So what does that mean practically for the people building these AIs?
It means they get what you could call a free lunch with their training data. A traditional model, you'd have to show it a molecule, then show it that same molecule rotated 100 different ways just to teach it that rotation doesn't change the physics.
Which is incredibly inefficient.
Massively. But EGNNs, because they treat molecular features as these highly specialized mathematical objects called spherical tensors, they inherently understand how rotation works. It's baked into the code. They don't need to learn it.
Wow. That's a huge shift. You're using pure physics as a kind of an inductive bias for the deep learning.
It's a remarkable fusion of abstract math and computational biology, and having this powerful foundation immediately lets us move beyond just simple static thinking.
You mean moving from a photograph to a movie, right?
Exactly. Historically, you had these incredible models like the early AlphaFold versions that would give you a single perfect static state, a snapshot.
Like a crystal structure.
Right. But biology isn't static. Proteins are dynamic machines. They're constantly changing shape. Think about the SARS-CoV-2 spike protein. It has to open and close to infect a cell. You can't design a drug against a single fixed version of that.
So you can't design a key if the lock is constantly shifting its position.
You can't. And to solve this, researchers developed the distributional graph transformer, or DAG. And the goal of DAG is conceptually huge. It aims to predict the entire equilibrium distribution of a molecular system.
Okay, wait. Not just one snapshot, but the whole probabilistic cloud of all the states it could be in?
All of them. Stable states, transition states, everything in between. It uses a reverse diffusion process to sample this cloud so it can actually generate new conformations that have never been seen in an experiment but are guaranteed to be physically possible.
Can you give us an example where this really outperforms the older models?
A great one is human BRAF kinase. It's a cancer signaling protein, and it has multiple stable forms, like an active R state and an inactive off state.
And the older models struggled with that.
They struggled to resolve that off state. DAG, on the other hand, can easily and quickly sample both structures. It shows it understands the full range of native motion.
So if we put this all together, if we combine this physically aware AI, the equivariance part, with this dynamically aware AI from DAG, it means we can finally build generative models that can reliably engineer totally new molecules.
And that brings us to the flagship model demonstrating this, BoltzGen.
Which is a true breakthrough.
It really is. It's an all-atom generative model designed for universal binding. And it's not just for proteins. It can design nanobodies, cyclic peptides, helical scaffolds.
Against all sorts of targets too, right?
Yeah.
Proteins, small molecules, nucleic acids.
Exactly. And the input isn't just design a binder. It's what they call a flexible design specification language. You can tell it you need certain covalent bonds or that it has to target a very specific binding site.
Okay, let's walk through the pipeline. Because the process itself is what builds the confidence. BoltzGen generates a candidate molecule. And then what happens?
After that initial diffusion generation, it goes into refinement. First, there's an optional step called inverse folding. That just helps clean up the amino acid sequence to make sure it's chemically sound, soluble, likely to actually fold in the real world.
And the next step seems like the real acid test for stability.
It is. It's the refolding step. They use a totally separate structure predictor, Boltz2, to see if the binder they just designed can fold stably on its own.
So you take away the target it's supposed to bind to.
You strip it away and ask, is this new thing a stable entity by itself? If it just collapses, it's useless. It's a non-starter.
And then finally, you check to see if it actually sticks.
Right. The final steps are analyze and filter. They compute all these physics-based metrics, hydrogen bonds, buried surface area to quantify the binding strength, and then they rank everything to get the best candidates.
And the validation data is what makes this so compelling. This isn't just simulation. This is the wet lab. BoltzGen achieved nanomolar binder success rates for 66% of 9 novel targets.
That 66% number is just a watershed moment. And crucially, those were truly novel targets. Less than 30% sequence identity to anything we've seen before in the entire protein databank. The AI had to invent, not just copy.
That proves it works on uncharted territory. That's a huge hurdle to clear.
It is, and there's a great example. They used it to design proteins to neutralize antimicrobial peptides, which are notoriously hard to target. One of the designs, Indo4, was validated with surface plasmon resonance at a remarkable 0.22 micromolar KD.
So you're designing a stable, high-affinity therapeutic candidate from scratch.
From scratch.
But the success immediately brings up that fundamental question of trust. If we're inventing things that have never existed, how do we know the AI's imagination actually lines up with reality?
That is the elephant in the room. And it raises this really important question because our traditional confidence metrics, even something as good as AlphaFold's PLDDT, they can suffer from what people call hallucination.
Meaning what exactly?
Meaning the model gives you a high confidence score for local little segments, suggesting they're well predicted, but the overall structure has these subtle, devastating errors. Parts of the protein might be clashing or just spatially impossible.
So the old metric only looks at the local fit.
Yeah.
We need something that looks at the overall coherence of the design.
Yes. And this is where this new framework, CONFIDE, and its component come in.
Okay, so what is CONFIDE doing differently?
CONFIDE unifies two different types of complexity or frustration in the protein folding landscape. You have the one we know, energetic frustration, which is what PLDDT is good at. Are the amino acids right next to each other happy?
And then there's the trickier one, topological frustration.
Exactly.
Can you give us an analogy for that? What is topological frustration?
Think of it like assembling a huge piece of IKEA furniture or tying a really complex knot. Energetic frustration is like checking if a screw between two adjacent boards is tight.
Okay, that makes sense.
Topological frustration is assessing if the whole thing is going to stand up. Are the long connecting pieces aligned correctly? Is the entire knot so tangled and strained that it's about to pop? It's about the long-range structural integrity.
So it's about the entanglement of the whole protein backbone.
Yes. And that is what CODE, which stands for Chain of Diffusion Embeddings, actually measures. It's extracted directly from the internal latent states of the model's own diffusion transformer.
So you're using the model's own internal thought process as a quality control check.
That is such a smart way to put it.
Yes.
You're watching its reasoning path. And it's a massive improvement. CODE has a correlation of 0.82 with actual folding rates driven by this topological frustration. PLDDT is only 0.33 on the same metric.
Wow.
CODE sees the knot forming, where PLDDT just sees that the local bit of rope looks fine.
And when you put the two together in CONFIDE, the reliability just takes a quantum leap. We saw data that it hit a correlation of 0.73 with the gold standard RMSD for predicting these complex molecular glue structures. PLDDT was at a miserable 0.42.
That's a 74% improvement. It makes the novelty trustworthy. And its real-world use is profound. Beyond just better design, it's a diagnostic tool. When they used it to predict BTK inhibitor resistance.
The huge clinical problem.
Huge! CONFIDE's prediction of affinity changes correlated with the experimental data at 0.83. PLDDT's correlation was basically zero. It lets you anticipate drug failure.
And if we connect this to the bigger picture, you can't build a trustworthy AI without trustworthy data to begin with.
Absolutely not. And a key resource driving this is the PPBI database, the Predicted and Experimental Peptide Binding Information Database. They curated 329 peptide protein complexes and paired them with experimentally measured thermodynamic data.
And why is pairing the structure with the thermodynamics so important?
Structure tells you where the atoms are. Thermodynamics, a delta G, delta H, delta S, that tells you why they stay there.
Yeah.
It's the energy reward of the binding. Training on both lets the AI learn not just the geometry, but the underlying physics of stability.
And the criteria for getting into this database were incredibly strict.
They had to be high-resolution structures only, and critically, they used other computational tools like Rosetta Fold to refine and fill in any missing bits of the structures. So the AI is only trained on the most complete, most accurate data possible.
Okay, so designing a high-affinity binder is one thing. But if it melts in your bloodstream or it's toxic, it's a useless drug. We have to talk about developability.
Right. This secondary vetting step is essential. This is what moves a design from a lab curiosity to a real therapeutic candidate. And that's the domain of platforms like Peptiverse.
What's Peptiverse focused on?
It's a unified platform for predicting multiple peptide properties: hemolysis, solubility, toxicity, stability, all of it.
And what's unique about it?
Its ability to handle chemical modifications. It accepts both standard amino acid sequences and chemically modified peptides that are represented by smiles. And that's huge, because peptides are often changed chemically to improve their half-life in the body. If your platform can't assess those versions, it's out of date.
And the developers found a really interesting bottleneck, didn't they?
They did. They found the limiting factor wasn't the final classifier model that says toxic or not toxic. The bottleneck was the quality of the underlying representation from the foundational model, like ESM2, that turns the molecule into a mathematical vector. Better representation means better predictions, period.
Now, moving from the binder back to the target. Even the target itself can be elusive. We have to discuss the challenge of cryptic pockets.
Cryptic pockets are fascinating. These are binding sites that are completely invisible or closed in the normal, unbound protein structure. They only open up when a drug or a ligand starts to interact with the protein.
So if they're hidden, how on earth do you find them? You can't just look at a crystal structure.
No, you need these advanced, computationally expensive, enhanced sampling simulations. If you just run a standard molecular dynamics simulation, these sites are too unstable and they close right back up. You need sophisticated techniques like swish to capture those fleeting moments when the pocket is open.
So the existence of these pockets suggests it's a mix of binding mechanisms.
Precisely. It's an interplay. It involves conformational selection, where the protein just happens to flicker into that open state, and induced fit, where the ligand itself forces the protein to change shape. The challenge is designing a molecule that exploits that entire dynamic dance.
And to bring this all back to a real-world therapeutic context, we can see the power of this by looking at the success of GLP-1 receptor agonists.
Yes, the drugs used for diabetes and weight loss. The sheer scope of their effect really highlights the potential here.
And the key was recognizing how broadly distributed that receptor is.
Right, especially in the central nervous system. That's why the Alzheimer's trials using these GLP-1 drugs don't require participants to have obesity. It shows the neurological and metabolic mechanisms are distinct pathways that are just responding to the same drug.
And you mentioned there's a quiet revolution happening in these big clinical trials now.
It's a total game changer. Proteomics. During the trials, researchers can now analyze thousands of circulating plasma proteins in real time. This gives us completely new molecular insights into how the drugs are working, like how they reduce major adverse cardiovascular events, or MAE.
which could lead to more personalized medicine.
Exactly. This kind of data could let us move past these generalized treatments and start classifying different molecular types of obesity.
This entire deep dive has really shown the molecular design landscape transforming. We've moved from just looking at nature's fixed structures to actively designing dynamic molecules,
And ensuring they work.
ensuring they obey physics through symmetry, that they fold correctly with pipelines like BoltzGen, and that they're viable as drugs using platforms like Peptiverse.
The core shift is leveraging AI not just to model reality, but to actually invent viable solutions to some of biology's hardest problems. We now have the tools from these equivariant networks to confidence metrics like CONFIDE to really trust the design process itself. We can assess both energetic and topological fidelity before ever stepping foot in a lab.
Which brings us to a final provocative thought for you to consider. If AI can now predict the entire equilibrium distribution of a target, showing every stable and unstable state, and new metrics like CONFIDE allow us to confidently assess highly transient designs, like those targeting cryptic pockets. How will drug discovery move beyond targeting static protein crystal structures and fully embrace designing binders specifically for the entire time-dependent probability cloud of molecular systems?